there are 4 topics, 4 themes that you have to do. Everything is in your textbook, but one is surface tension, the other is specific heat, third, these 4 themes you are going to learn: surface tension, specific heat, resonance, the phenomena of resonance, and electron-specific charge. Yeah? Some of you might not be familiar with these topics, but of course that's why you are going to learn this, right? And some of the themes contain quite a lot of mathematics. Yeah? So please be prepared. At least, please do not panic. Yeah? I will explain that before showing these mathematics. And I'm sure that you can understand in the end. Yeah? In the end. So these 4 themes, and these are experiments. You can actually do experiments to measure, for example, surface tension of water, or specific heat of materials you are given, or things like that. You do that. And please make please make a pair. To do one experiment, yeah? Because some experiment needs to separate tasks. Maybe one student read the gauge and one student record the number, things like that. So you have to make a pair. But of course, as far as I know, the number of students are odd. So some group must be, なんていうの, three months, three students. Yeah, that's okay. So make a pair. And change the pair. Change the pair when you finish one experiment and to proceed on the other. Yeah? Okay. You choose your pair, right? So please just make a pair, but you finish one experiment and go to another experiment, you have to change the pair. Yeah? So you will be 4 students as your pair. Okay? And the third point, do as many okay, because there are only 4 days, and we have 4 themes, and today will be used for explanation and introduction. So you don't have time to do one theme per day. That's not possible. You have to do at least 2 themes in a certain day to complete 4 themes. Yeah. So please, if you finish one experiment earlier than you expected, maybe, just proceed to do other experiment. Yeah, you're free to do that. Please ask questions. And okay, the last one I forgot to mention. 5, make a report. Make one report. Per theme. In the text here, everything is described here in the text, and including the report you have to write after the experiment. Yeah. So, for example, can you look at the page? For example, can you look at the page number 79? This is an explanation about surface tension measurement, and there is a section where you can see that the report should be like this. Make a graph of Z versus M, calculate the spring constant, make tables of measured values and their means, and estimate the surface tension of water and compare it with known values, such a thing. Please make one report per theme, like this. Please answer everything here in the textbook. And the deadline of the report will be informed later, but maybe next New Year. Yeah? So usually you have, say, 1 month to complete your report, but you don't have any chance to repeat the experiment usually. Of course, if you want to do that, please just let me know. So please do experiment in this schedule, within this schedule. Please finish it. Then you can make your report. Yeah? Okay, this is an introduction of the course. Do you have any question? Yeah, please. Sorry?
Is the report due per week?
Sorry, say again.
Is the report due
Per
per week?
week?
Like one report for...
No. After finishing 4 themes, you are asked to submit your all 4 reports within a month or within 2 weeks or things like that. Yeah? But I recommend you to finish one report immediately after you finish one theme, of course. Yeah? While you remember everything well. Right. Oh, another thing is, so this means that you have to make a note about what you did. Yeah? And things, please make sure that you look at the introduction. This material contains a certain introduction about experiments. Yeah? The chapter 1, general introduction, and there contains basic knowledge of experiments, like units, accuracy, how to make a graph, how to write a report. Yeah? So please make sure that you look at these introduction. And taking your note in detail is very important. So everything you did must be recorded in your notebook. Yeah? Then you can write your report with consulting with your notebook. Okay. So then, sorry. So far so good. And today, because last year we did the same thing to your second year student, and it was such a disaster that because some of you don't have any experience to experiment. Yeah. So I will explain it before you do it. I will show you how to do it actually, using actual apparatuses. Yeah? So today I will do that, all 4 themes. So it's a very quick introduction of the themes, and please concentrate. And you have to remember every motion that I do. Yeah? Well, first introduction. Have you ever heard that what the surface tension? Do you know surface tension? No? Well, but as a general property, a surface wants to shrink. That's a general knowledge. If this surface is how to say mobile, soft, and deformable, the surface always wants to shrink. That's the property. So if you have like rubber seed, it will want to shrink. And how strong is it? Is a surface tension. And of course, this is physics. We have very precise definition of the concept, like surface tension, and which is, if you quantify how strong this surface wants to shrink, you have to measure the force per unit length. Now the first equation appears here. Surface tension is force divided by unit length. So if you make a slit here, you cut 1 centimeter. Then this cut, because now surface is broken discontinuously, then it will go this way. This part go this way, and the other part go this way. Yeah, because of the cut. Then you can measure this force and divide it, and the total force, and divide it by the length of the cut, which is the surface tension, which gives you the surface tension. And we use the symbol, it's gamma. In physics, you find many Greek symbols like gamma. So please don't be afraid about that. This is just a symbol, because this is just because I don't want to write surface tension every time I mention. Yeah, that's why I use gamma. That's it. That's a very stupid reason. So please do not afraid this symbol. It's just a letter. Yeah. Okay. So this is the concept of surface tension, and you are going to measure the surface tension of water. So this is a concept, and the method. Let me make it a bit hurry. Method is quite easy. Well, in principle, you can measure the surface tension if you make a surface like this. Let's say this is a soap film. Yeah. And this is a wire. You can make a film like this. And if you can pull one side of the film by a certain force. And if you divide this force by the length between the two, it will give you the value of surface tension of this film. This is a principle. But this is not easy to do it. Well, soap film, maybe you can do that. But water, it's difficult to make a film. So, in practice, we use a plate, metal plate. Actually, this is, actually, this is just an, stainless plate. But in real experiment, real lab work, we use platinum plate. So usually the apparatus to measure surface tension is very expensive. But this one is not. So, but still do not break. Yeah? Be careful. Then you touch this plate to water surface and pull it. Then this plate will pull. This is water. This plate will pull the surface of the water. Yeah? Then surface tension pulls back, pulls down, pulls this plate down. So if you apply a certain force here, if you observe that this plate is fixed, which means that this force is balanced by the surface tension. Yeah? In this way, you measure the surface tension. This is a principle. But in the text, there is another factor here. Because the deformation of the surface is quite large, especially for water. Water has a very strong surface tension. Then that's why you can pull up a certain amount of water upwards. So this body of water has a gravitational force by gravity. You have to consider this as well. So in principle, this is not the answer, but in principle, this must be 0. Sorry. If you observe that, okay, this plate is stabilized, then the force here, force here, force here, in total, it must be 0. Yeah? Do you know why I multiply the length of the plate? The length where, okay, let's say let's observe this plate this way. It's actually it's a ring, but let's say this is a plate, and this plate wet and pour the water a certain amount. L is the length here. Do you understand why I have to multiply L to gamma? Anybody? The one? This?
Because it always different with one practice. No, I don't know.
No, come on. You're saying quite right thing. Well, because gamma, surface tension, is defined by the force, defined as the force divided by length. So here, these are force. So in order to make this term a force, you have to multiply the length. Gamma is some force divided by length. Yeah, so this is a practice. So it's actually a ring. This plate is actually a ring. So the length L is actually it's a tube. I will show it. Like this. Like this one. Yeah? So you have to measure the length around the ring, which means this is 2 pi r. If this is actually this is R1. Sorry, I don't remember which is R1 and which is R2. But you know the surface is exists both outside and inside. So L2 must be considered as well. That's the length. Yeah? So you make an equation to measure, actually calculate the surface tension. And how to measure the force? Measure F. Please ask any question anytime if you have. It's easy. We use a spring. Yeah? Like this one. And if you apply the force to this spring, yeah, it will be elongated. And this length is proportional to the force you apply. Yeah? Force is proportional to the position of a certain point of the spring. If you define a certain point as an origin, usually it's a still point. In this apparatus, you have this wire here. And actually, this is a mirror. And on the mirror, you can see the scale so that you can measure the position of this wire. And when this, in this state, nothing is moving, then you define the origin here, like now 27 centimeter point something. Yeah? Then the length the length of elongation, Z, is proportional to the force applied. And the proportionality constant, K, is called a spring constant. Yeah? So, this way you measure the force, which means that before doing experiment, you have to, how to determine K, the spring constant. You must know the value of K in order to interpret the position of the spring as a force. Yeah? But that's easy. Oops. So before doing any experiment, right, there is a mass here. There are four sets of mass and tweezers. There is tweezers, and you just, oops, this is a bit, just put a certain mass. This is, sorry, I can't see it. This is 5 gram. So now you, あれこれどこに? Okay, whatever. You define the origin here, maybe. Then you put a mass, 5 gram mass here. Then it will go downwards. And you have to wait a certain time to make sure that everything is still. Then you measure the length for this mass. So 5 gram, like 5 gram, give you this length, like 2 cent. Yeah? And then you repeat this experiment, like 10, blah, blah. So you have this kind of plot. Then you can make a line, and this slope. Oh, sorry. You can measure the slope. And actually, the mass, any mass, produces a gravitational force which is proportional to the gravitational acceleration z, which is 9.8. This is known. So actually it's a bit less than 9.8, but please use this value. So interpreting this graph is something like this. And this slope gives you the spring constant. Yeah? Then, or maybe you can just use this graph as a metric to measure the force. But anyway, in this way, you can interpret the position of the spring as a force. So, then, actual force balance is you measure it becomes like this. This is plate, surface, well, spring produces the upward force. Its F up is, let's say, Kz. Well, and this is the mass of spring. Mass of the ring. Sorry. Then F down is firstly the mass of the ring. Mass of the ring times gravitational constant, which is a gravitational force. It's this one. So you push. Yeah, this mass pulls the spring downwards. And the surface tension creating downward force on the outer surface of the ring and inner surface of the ring. This is the surface tension. Plus the volume of water here. This volume of water pulled by the ring, well, which is calculated like this. The density of water this is the volume of water. And h is the height from the surface. You can estimate this volume like this. And the reason, please just consider. And yeah, so this is a gravitational pull by the water pulled by the ring. And the force balance, if you see you see no motion, there must be force balance. And everything except the value of gamma should be known. Then you can calculate the surface tension. Yeah? And for students who are really confused, actually, you can maybe just omit this term. That's very small. You know, the volume of water pulled by the ring is quite small. This is a kind of additional term. So maybe it's a good idea that you just ignore this term, calculate the gamma by this equation. Then after that, you can consider the correction given by the water volume here. Yeah? And maybe you can compare the two values. Yeah? Okay. So, wow. Actually, this stage is movable like this. And 久保さん、ちょっと水を。ありがとう。You just pour this dish, pour water to this dish. But before that, please make sure that it's clean. There is an ethanol. You have to clean up everything. No? Because surface of water is easily contaminated by any dust, anything. So you have to wash this dish by ethanol before you do the experiment. But anyway, now if you, if you rotate this, it's a micrometer, we call it. It will go up, then. So for a rough motion, you use this stage, entire stage. And this controls the subtle motion of the stage. And now it touches, the ring touches the water. Then, because you want to measure the height in order to calculate this term, yeah? So you record this value, then you pull. Can you see the water surface deformed by the pulling? Actually, water has a quite strong surface tension, and the deformation can be quite a bit. Still, like 2 or 3 millimeter, you can pull. Then, of course, you have to you have to measure the position of spring as well. And you measure the maximum position, this position. And just before that ring detached from the surface, you measure this position. Now, you measure that. Then the position of the spring gives you the force applied by the spring upwards. Yeah? That way you measure this term, and you calculate the downward force using this equation. It will then you equate these two terms, and it will give you the value of surface tension. Easy, right? Any questions? Okay, so using these 4 apparatuses, we measure specific heat of a solid, like that one. Yes, thank you. Like this one, quite heavy. Yeah, and there are 4 different types of solid, like that one. Can I get one? Yeah, that one. Thanks. Yeah, well, for these two, it looks similar, but the color is slightly different. And each pure material has its own value of specific heat. But before that, what is specific heat? is heat necessary to raise the unit temperature in this case 1 degree of the unit mass. Of course, you know that you can warm anything if you have a heater. Yeah? But how much energy you have to put to warm it up depends on what kind of material it is. That gives you the specific heat. So let's say this is a solid or anything, not necessarily solid, but in this case it's a solid, and its temperature is T0 at first. Then you give it the heat, a quantity of energy. The temperature goes up to a certain value, T1. So now this amount of energy, heat, was necessary to raise the temperature from this value to this value. You observe that. Then specific heat is defined by this. Because it's specific heat is a certain quantity characterizing a material. So it's normalized by the mass. It's a unit mass. Then you have to divide the energy by mass of the body, and this is a temperature difference. Because the specific heat is necessary to raise the unit temperature. Yeah? So you have to divide the energy both by mass and the temperature difference. That's a specific heat. Quite simple. That's a definition. You cannot argue that. This is it. No question is accepted about that. We define that as it is. So, but the problem is how to measure it. But it's quite simple. And actually, this is the method, Ebris calorimeter. We call it this type of a plate as a calorimeter. Okay, this is a sample, which mass is ms, whose specific heat is C sub s, and whose temperature is Ts initially. This is a sample. And you prepare a cup, within it water. Cup has a mass, mc, and specific heat, cc, and the temperature, tc. Actually, that's this one. This is a cup. It's actually copper cup. And water, water has its mass again, and specific heat, and temperature. But because inside this cup, water is already in, because of this situation, the temperature of water is the same as the temperature of the cup. This one and this one is the same. You prepare that. Then, but the temperature of the sample and the temperature of this, we call it calorimeter. Temperature of the sample and the temperature of the calorimeter is different at first because we warm it up, because we, this is a heater, and using this heater, we warm the sample up. So the Ts is larger than Tc. Then you put the sample inside the calorimeter. The sample. And you mix the water slowly and wait. Wait until the temperature of the sample and temperature of the calorimeter becomes the same. Yeah? Then at the final situation, we call it an equilibrium. Final temperature is TE. Well, in principle, it's easy. Then, but if you think that why so? Why the temperature at first different? At first it's Ts and Tc. Sorry, this is S. Becomes the same temperature. The reason why is that the energy the sample has at first is transferred into the calorimeter. So the sample gives its energy, and calorimeter takes the sample's energy. Yeah? And if you wait long enough, it will be balanced. Initially, the energy, this situation, everything has energy. Heat is something like this. Mass times temperature times specific heat gives you an amount of energy. Plus cup, Tc, Cc, plus water, Tw, sorry, no, it's Tc, Cw. Initially, these three parts have this amount of heat, and which is finally which becomes the same temperature the final state is like this. The temperature is the same, but anything else like specific heat or mass does not change, of course. Only the temperature changes. And if you can assume that any heat escapes from your box, actually this box, no leak at all, these two must be the same. It's an energy balance. Energy total amount of energy does not change. Yeah? So you can equate these two formula. And in this equation, this one, this one. This is the only quantity you don't know, because you don't know what the material is, what kind of solid here you have. But other things you can measure, or you know. You can measure the weight, the mass of the sample, temperature of the sample, mass of the calorimeter cup, and temperature of the cup. And this is the specific heat of the copper. You can find the value, the quantity, the value in your textbook. The specific heat of the copper is given, and this is water. Specific heat of water is also given. So you measure the mass of water, temperature, but these C and CW are known. So in the end, this is the only unknown parameter. So if you can do this experiment, that is, you measure the TS, this is a measurement. And you measure this, and you measure the final temperature. CS becomes the only parameter you don't know. Then you can calculate the value of the CS, which is the specific heat of the solid. Yeah? And in practice, what you do is something like this. You make a graph. But before that, I will explain how to operate it. So this is this box is a controller of the heat. You can see the temperature, I guess. Yeah. 90 is the set temperature, and this 18 now is the temperature inside the heater. So now it's raising, yeah, until the temperature inside becomes 90. So you wait, and you put this sample into the heater. Make sure that it doesn't touch on the wall of the heater. This is a pipe. So if you wait long enough, like 20 minutes maybe, you have to wait. Well, that's an experiment. You just wait. Then the temperature of the sample will become 90 degrees after 20 minutes. Yeah? So TS is 90, right? And meantime, you make the calorimeter. So inside this wood box, there is an heat isolator. This pipe, entire pipe, has a space inside, and which isolate the inside from outside, and you hang this copper cup. And within this copper cup, there's a water, But make sure that you measure the weight of water and copper cup as well. So this kind of thing. And you put the calorimeter in this isolation wall. Yeah? Then I will put it back here. 痛い。あたたたたた。あ、ちょっと引っ張って。痛い痛い痛い痛い痛い。よいしょ。Thank you. Thanks. Right. So what the temperature is now?
29 or 30.
30. Well, of course you have to wait until it will become 90 degrees. But now I will do it, nonetheless. So, yeah. This is an...
Sorry.
Yeah, no problem. So there's another thermometer. So now the temperature is like 18.8. And this is a probe. And you insert the... What's wrong with that? Yeah,
Okay.
yeah, okay. Apology accepted. And you see that this is a stirrer. You have to gently stir the water during the experiment in order to homogenize or make sure that the temperature is the same. Yeah? So, then you drop the sample inside the calorimeter. There's a lid here. And if you slowly drop the sample, here you can see the temperature. And make sure the sample doesn't touch the cup. So I hope that temperature will increase. I don't know. Then, this way, starting from the given temperature, Ts, 90 degrees, and of course you have to measure the initial temperature of cup and water, Tc, like 18 degrees. You can measure the entire temperature change in the course of experiment. The x-axis is time, t, like second. Like second, and temperature, degrees Celsius. Then, at first you measure, say, 5 minutes, the temperature of the cup by this thermometer. Then you put a sample here in this instant. Then the temperature will go up and reach at maximum, then slowly decreasing. That is expected. You can imagine that. Then what we have to, we must know is the equilibrium temperature. But the problem is that if you wait long enough, the temperature is anyway going down until it reaches at the room temperature. So we assume that this equilibration takes quite quickly. So probably if you extrapolate this line into this moment, T0, this is the moment you drop the sample into the calorimeter. Then this temperature gives you TE. That's the method. And everything is, of course, described in textbook. Don't worry. But in this way, you can measure the TE here. But in order to do so, you have to make a graph, temperature versus time graph, to measure this value. And this is TC. And because you know T sample, TS, everything, every parameter except CS are now known. And to measure the weight, the mass of the sample, please use scale here. Yeah? Ask me or ask Go-san how to use it. Okay? This is how to measure specific heat. Any questions? You can do it, I hope. Yeah? Right. So we have two more things. I have two more explanations. Yeah? But before that, let's have a break. And